gonna show how to build and train a variational autoencoder using PyTorch. Now, variational autoencoders is a type of generative models, just like generative adversarial networks, for example. Then I'm going to show how you can use this model to generate digit images. Now, I created this variational autoencoder in relation to a work on semi-supervised learning. So I'm also going to show how to use generative models, and particularly this time variational autoencoder, to do semi-supervised learning. I want to mention that this is not a tutorial on variational autoencoders or machine learning. You can of course search online for such tutorials. One good course about deep learning is one offered by New York University Center for Data Science. I think it's a very nice course and you can follow it. And there is also a section about variational autoencoders. Much of the code here is taken from the examples they provide in the course. This will help you if you want to see how things work end to end, or maybe you just want to get some code that just works, and then you can build on top of it, whether you are working on a project or whether you just want to build a variational autoencoder that generates some kinds of data you're working on. Now, there will be a link to the code, so I'm not going to write the code here, but I'm just going to provide some kind of a quick walkthrough over the code. Now, I'm running this using Google Colab just because it makes it easier to run these kind of Jupyter notebooks without having to install anything on my machine. So I start with some imports from PyTorch, and then I also import matplotlib for plotting some figures, and also I import NumPy. Then I have some helper functions to help set some pyplot defaults and also plot some images. After that, I check whether GPU support is available. Then we can run our training on a GPU, otherwise we'll revert back to CPU. Now, I'm using the MNIST dataset, and when using PyTorch, it's very easy to download the dataset and load it. So I create loaders just so they take care of shuffling the data and loading it in batches and so on. Once the data is downloaded, I'm going to plot some images from MNIST. Now, in my experiments, I'm not using the original MNIST dataset, but I'm using the binarized MNIST, and that's why I'm applying this binarizer. Now I'm going to plot some binarized samples. As you can see, compared to the original samples, if we take a look at the original samples, you can see those look more crisp than the original samples because now the pixels are either 0 or 1. Now we get to the variational autoencoder. Now I keep the encoder and decoder to a very simple model. So I use a sequential model for the encoder and also for the decoder, just a sequence of linear layers and activation functions. Now the encoder is a function that maps the input of size n, which is here 784, to the hidden representation. Now the size of the latent vector is 20, as you can see here. But the output of the encoder is double this size, because the output of the encoder is not really the latent vector, but rather it is the mean and the variance of the distribution that the latent vector follows. And that's why you will see later that we need to sample from this distribution in order to get the latent vector. Now, as I've just mentioned, to obtain the latent vector, we need to sample from the distribution produced by the encoder. And this is a little bit problematic because when we do gradient descent to train the variational autoencoder, we do not know how to do backpropagations through a sampling module. So that's why the reparameterization trick is necessary here, so that backpropagation in training is possible. And specifically, the gradients will go through the element-wise multiplication and addition in this equation here. Now, during training, we encode the input x into the hidden representation. Then we sample the latent vector z, which is then passed into the decoder. This will get us to talk about the loss function, because in order to perform the last step, we need to either learn the distribution of the latent vector or enforce some kind of distribution. And this what characterizes variational autoencoders, because we do enforce a Gaussian distribution to the latent space by adding a regularization term to the loss function. And that's why the loss function here is a sum of the reconstruction loss and also KL divergence loss. You can read about KL divergence. It's essentially a measure of how one probability distribution is different from another probability distribution. So I'm going to regenerate some images before we train the model, just so we see that they will be basically noise. So as you can see, the generated images are just noise, and now we can compare them to the images generated once we train the model. Now I'm gonna run the training loop for 50 epochs, and then we're gonna test the trained model and see how good the generated images will be. Now training is over, and we can see how the reconstructed images look like in the first epoch. as the epochs go forward, we can see that reconstructed images are becoming even better and better. And we can see toward the end of the training, the reconstructed images looks even better. Now, one good tip is to save the trained model so that we can load it later without having to retrain it again. Now I'm going to try to generate some samples from the model to compare the trained samples after training with those we got before training, which they were essentially noise. Now you can see the generated samples. They look okay, I would say, because they are just generated from these random vectors chosen from the latent space and then run through the decoder to get back the generated images. Now when I plot the latent vectors in the latent space using a t-SNE, which is a dimensionality reduction technique, we can see how the latent vectors that kind of characterize the same digit, they are clustered together in this latent space, which kind of makes sense, of course. Now I'm gonna briefly explain how to use a variational autoencoder to do semi-supervised learning. Now, one of the common approaches in semi-supervised learning using generative models is to use the latent representations of the data for the classification task instead of the data itself. So this means that we take the original data, then we run it through the variational autoencoder to get the latent vectors, and then we do the training and the evaluation over the latent vectors themselves, not the data. So what I'm going to do here is to take a subset of the database, only 100 images, and then I'm gonna compare two classifiers. One classifier, it will not use the latent representation, it will train over the original data itself, the images themselves, and we're gonna train it over the 100 images. Then we're gonna evaluate this model over the test dataset. And then I'm gonna build another classifier over the latent representation of the data, also train it over the 100 samples only, and then test it over the test set to compare the results of these two classifiers. Alright, so as you can see here, I created a subset of the data set of 100 samples only by taking 10 images from each class label that we have here. Then what I'm going to do is to use the encode method of our trained model to convert the data to the latent representation. Now here I'm going to create a simple linear classifier with only one linear layer so that we can use it to train over the latent representation. For the optimizer, I'm going to use Adam again, and also for the loss criteria, I'm going to use a negative log likelihood. And as I said, we're just going to train this classifier over the latent representation of this data composed of 100 samples only. And then we're going to evaluate the performance of the model over the whole test dataset. So now training is over, and we can see that we have achieved an accuracy of 42%, meaning that 42% of the images were classified correctly on the test set. Now the baseline model is another simple neural network, a sequence of linear layers and activation functions. I am also going to use the negative log likelihood as a loss function and stochastic gradient descent as the optimizer. Now I'm going to run the training loop for 100 epochs just like before and see what kind of accuracy we get with this model. Now training is over with the baseline model, and we can see that the accuracy that we've achieved is 11%, which means only 11% of the test set images were classified correctly. Now we can conclude that when doing semi-supervised learning, meaning when there is only a small subset of the data that is labeled, and then we want to use this subset to label the unlabeled data, then we can see that a semi-supervised approach using the latent representation of the data, which we have obtained using a variational autoencoder, performed way better than a model that was trained over the data itself.